You ever think about how, like, math, it seems like it should be so straightforward, right?
Yeah.
Like 1 + 1 = 2.
Exactly.
There shouldn't be, like, room for debate.
Right.
But it's amazing when you dig a little deeper.
Oh,
You
absolutely.
find out, even in, like, the most fundamental areas of math, there have been some like, huge philosophical disagreements.
Oh, yeah. Some really, really foundational disagreements.
And that's exactly where our deep dive takes us today.
Okay, let's do it.
So we're going back to the early 20th century
Okay.
for this, like, captivating intellectual battle between two giants of mathematical logic, Gottlob Frege
Frege,
and David Hilbert.
Hilbert, two of the biggest names. Yeah, absolutely. And what's really fascinating about their disagreement is that it wasn't about some, like, minor technical point, you know?
Right.
It wasn't just like, oh, they missed a minus sign or something.
Yeah.
It was about how they understood the very building blocks of mathematics. Axioms, and like how we know that a system of axioms is going to be like, okay.
Right, yeah.
That it's not going to lead to contradictions.
Right, and that's so important.
Right.
Because if you have a system that leads to contradictions,
you can prove anything.
Yeah, you can prove anything, and then, like, what's the point?
It's all meaningless.
Exactly.
Exactly.
So that's consistency.
Yes.
And then there's the idea of independence.
Right.
That each axiom is kind of bringing something unique to the table.
Exactly. Not just a byproduct of the other ones.
Okay, so in this deep dive,
yeah,
we're going to unpack this whole Frege-Hilbert controversy.
Right.
And we're going to focus on these contrasting views on axioms.
Okay.
And their different approaches to consistency.
Sure.
Making sure a system doesn't lead to, like, these logical train wrecks.
Right.
And then independence.
Yes.
Showing that no single axiom is just kind of like, following from all the others.
Right.
And the great thing for you listening is we're going to navigate this, like, potentially really complex terrain.
Yeah, it can get pretty hairy.
Without getting bogged down in, like, the overly technical stuff.
Yeah, we're going to keep it high level.
Yeah, so think of this as, like, your express lane.
Fast track.
To understanding this, like, pivotal moment in the philosophy of logic and mathematics.
And it really is a pivotal moment. Like, so much of 20th century mathematics and logic flows from this debate.
Totally. And I think, any philosopher who is interested in, like, the foundations of these fields really needs to grapple with this stuff.
Absolutely, because it really exposes, like, different ways that we can conceive of what mathematical truth is even.
Right. And what these, like, mathematical theories, what they're all about.
Yeah, exactly. What are they actually doing? What are we trying to capture when we build these systems?
Exactly.
Huge questions.
So to help us on this journey, our primary source is the incredibly informative entry on the Frege-Hilbert controversy.
All right.
In the Stanford Encyclopedia of Philosophy.
A classic.
Yes, it's a great resource.
Yeah, it's really good.
For this. And it gives us a really detailed but accessible.
Yeah, they do a good job there.
Account of Hilbert's groundbreaking work.
Groundbreaking, absolute.
A reason of, like, super sharp critiques.
Oh, yeah, razor sharp.
And the, like, philosophical chasm that just separated them.
Two completely different worldviews.
Totally. Okay, so let's get into it. Let's start with Hilbert and his impact with his Foundations of Geometry.
Okay, so Hilbert's Foundations of Geometry, this was published in 1899.
Okay.
Really a watershed moment, I think, especially for philosophers.
Okay.
In how we think about mathematical systems.
Okay.
Now, it was about geometry, right? That was the immediate subject matter.
Sure.
But it had this influence that extended way beyond geometry.
Right.
To thinking about the role of axioms in, like, all mathematical theories.
Okay.
So it wasn't just a matter of saying, okay, here's, like, a new axiomatic basis for Euclidean geometry.
Right.
It was about changing how we even think about what an axiom is.
So it's meta in a way.
Yeah, totally. It's meta. It's about the nature of these foundational elements. Okay. And the encyclopedia really emphasizes his what they call structural approach to axioms as, like, the big revolutionary thing here.
Okay.
And he also brought this new level of, like, systematicity, I guess you could say, to investigating these meta-theoretical questions.
Meta-theoretical questions meaning?
Questions about the theory itself.
Okay, so not the stuff inside the theory.
Right, exactly.
But, like, about the theory as a whole.
Exactly. Like, is it consistent?
Okay.
Is it independent?
Got it.
These questions weren't just, like, secondary concerns for Hilbert. They were, like, central to his whole program.
So he brought this new level of rigor to these concepts, like consistency and independence.
Oh, yeah, for sure.
And as the encyclopedia points out, he defines consistency as this property That within a given system of axioms, you can't derive a contradiction.
Exactly. If you can derive a contradiction, the whole thing kind of falls apart.
It explodes.
Right.
So you got to make sure that doesn't happen.
Yeah, right. And independence, on the other hand, that means that a specific axiom or statement can't be logically deduced from the remaining axioms.
So it's not like extra or redundant.
Right. It's bringing something new to the party.
Okay.
And what's cool here is that Hilbert, he recognized this like really deep connection between these two ideas.
Between consistency and independence.
Yeah, exactly. Because think about it like this.
Okay.
If a system contains a contradiction, right?
Yeah.
In classical logic, you can prove anything.
Anything at all.
Yeah.
Like my cat is president.
Exactly right. And including statements that we might have thought were independent.
Okay, so a contradiction makes everything kind of meaningless.
It infects the whole system.
Right.
But on the other hand, if a statement is genuinely independent, adding its negation to the original axioms shouldn't create a contradiction.
Okay, so the way I'm picturing this is like a set of instructions.
Okay, I like that.
For building something.
Okay.
If the instructions are contradicting, like inconsistent, you could prove anything with them.
Right, you could prove that you're building a house and not a house at the same time.
Right, exactly.
It's all meaningless.
But if one instruction is like redundant, not independent, you could leave it out and still build the exact same thing.
It's not really adding anything new.
Okay.
So Hilbert, he comes up with this like very clever method for showing consistency.
Right.
And it involves what are called relative consistency proofs.
Relative consistency.
Yeah, so he wouldn't try to prove that like his geometric axioms were consistent just in some absolute sense.
Okay.
He would say, well, look, if we assume that some other theory is consistent.
Like a theory that we already kind of trust.
Yeah, one that's like more well understood, like maybe the theory of real numbers.
Yeah.
Then we can show that the geometric axioms are consistent too.
Okay.
So it's relative to this other theory.
Okay. And how did he go about doing that?
So the key here is this technique of reinterpretation.
Reinterpretation.
Yeah, so he would take the basic terms of his geometric axioms.
Like point line?
Yeah, point line lies on all of those good things.
Okay.
And he would reinterpret them using concepts from this other background theory.
Whose consistency was assumed.
Exactly. So instead of talking about like abstract points and lines,
Yeah.
he'd be talking about like numbers and sets and things like that.
So can you give me like a specific example of how that would work?
Yeah, sure. So one of his famous consistency proofs, he reinterpreted the term point as a particular type of ordered pair of real numbers.
An ordered pair of real numbers.
And a line became like a special collection of ratios of real numbers.
Okay. Okay, fine.
And the relationship was defined as like a specific algebraic relationship between these pairs and ratios.
Okay, so he's taking these geometric concepts and turning them into like algebraic stuff.
Yeah, exactly. He's translating geometry into the language of real numbers.
Okay, I see.
And the cool thing is if you can take all of Hilbert's geometric axioms and translate them into true statements about real numbers.
Through this like reinterpretation process.
Exactly.
What does that tell us about the consistency of those original geometric axioms?
So here's the logic, and it's really elegant.
Right.
If the original geometric axioms were inconsistent,
Meaning?
if you could derive a contradiction from them,
Right.
then that same contradiction would still be there after you reinterpreted everything.
Because you're just like changing the words, not the logic.
Exactly right. You're just changing the language.
Okay.
But now this contradiction would be a contradiction within the theory of real numbers.
Okay.
So if we believe that real numbers are consistent,
Yeah.
which we have pretty good reason to believe.
Because arithmetic seems to work pretty well.
Yeah, we haven't found any contradictions there yet.
Okay.
Then Hilbert's geometric axioms must also be consistent.
Okay, so their consistency is like relative to the assumed consistency of the real number.
Exactly. It's like a chain of consistency.
I got it.
And so the real takeaway here is that for Hilbert, the form of these relationships mattered more than the like specific meaning of point or line.
So it's not about what a point really is.
Not really.
It's about how these points and lines relate to each other.
Exactly. It's about the structure.
That's a big change from like how people had traditionally thought about geometry.
Huge change.
Okay, so that's consistency.
Yeah.
Now what about independence? Was that a similar kind of process?
Yeah, actually the method for showing independence is very similar.
Okay.
So to prove that some statement I is independent of a set of axioms, AX.
Okay, AX. Is the statement we're testing and AX are the axioms?
Exactly.
Really?
You got it. You would, again, reinterpret all the terms.
Like we did with consistency.
Yep. same idea, but this time you want to make sure that all the axioms in AX, when you reinterpret them, they become true statements within your background theory.
Okay.
But crucially, the statement I itself, when you reinterpret it, it becomes false.
Okay. So the axioms are all good.
You're all happy.
But the thing we're testing is not.
It's like an outsider.
Okay.
And this shows that I can't be a logical consequence of AX.
Because if it was,
it would have to be true.
If all the axioms are true.
Exactly. Yeah. So you found a way to make the axioms true and the statement false.
Right.
Which means they can't be logically connected.
So it's like finding a loophole?
Kind of, yeah. Like a weird universe where the axioms hold, but the statement doesn't.
Okay.
And that's how you show it's independent.
Got it.
So the encyclopedia points out that using interpretations like this wasn't totally new.
Okay.
But Hilbert's, clarity and how systematic he was about it, that was the big leap forward.
Okay.
And they say that when this approach was applied to, fully formalized languages, it basically set the stage for our modern understanding of models.
Okay.
In mathematical logic.
So he was really ahead of his time.
Yeah, he was a visionary.
Okay, so just to be clear,
yeah,
Hilbert wasn't just concerned with the rules within geometry. He was also asking these bigger questions about geometry.
Totally. Is this whole system going to blow up?
Right. Could we derive a contradiction?
Exactly.
Or are all these rules absolutely necessary?
Right. Are there any redundant ones?
So he's thinking about the theory from the outside.
Yeah, that's what we mean by meta-theoretical.
It's a theory about the theory.
Exactly.
Okay, and this whole idea of reinterpretation, it sounds pretty revolutionary.
It is. It's a big deal.
Like Hilbert saying that the meaning of terms like point or line isn't really what matters.
Yeah, it's a shift in focus.
What matters is the abstract relationships.
The structure, yeah.
Okay, and there's this great quote from a letter Hilbert wrote to Frege.
I love that quote.
Where he says, every theory is only a scaffolding or schema of concepts together with their necessary relations to one another.
Okay.
And that the basic elements can be thought of in any way one likes.
Yeah, it doesn't really matter what you plug in.
Right. And then he gives this really funny example.
I know, the chimney sweep example.
He says, if in speaking of my points, I think of some system of things, the system love, law, chimney sweep.
Love, law, chimney sweep.
And then assume all my axioms as relations between these things, then my propositions.
Yeah.
Like Pythagoras' theorem.
Right.
Are also valid for these things.
So it's like you can take these abstract relationships and apply them to anything.
Love, law, chimney sweep.
It's such a weird example.
It's a great example because it's so unexpected.
Yeah, it really drives home the point.
That it's about the structure.
The structure, not the things themselves.
Okay, so that's a good understanding of Hilbert's perspective.
I think so.
Now let's talk about Frege.
Okay.
He had a very different take on all of this.
Very different.
Like night and day.
Yeah. Complete opposite ends of the spectrum.
Okay, so the encyclopedia points out this fundamental contrast in their philosophical viewpoints from the get-go.
Right, from the beginning.
Frege believed that mathematical theories have a very specific, determinate subject matter.
Yeah, like number theory is about numbers. Geometry is about space.
Right. It's not just like these abstract symbols.
There's a real-world connection for Frege.
Yeah, and the sentences we use in mathematics.
Yeah.
They're important because of the thoughts or propositions they express.
About this specific subject matter?
So for Frege, it wasn't just about manipulating symbols.
Well, no.
It was about uncovering and expressing these mind-independent truths.
Yeah, these objective truths about the world.
Okay, so he thought these thoughts, they possessed a definite content.
Yeah.
And a subject matter.
They were about something specific.
Right, and they were either true or false.
Objectively.
With respect to that subject matter.
Exactly. And crucially, for Frege, these thoughts, they were the primary bearers of logical relationships.
What does that mean?
It means that for Frege, the thoughts themselves, they were what implied or contradicted each other.
Not the sentences.
Well, the sentences were just like expressions of the thoughts.
Got it.
So the real substance of a mathematical theory was in the thoughts, not in the symbols.
Okay, and this is where Hilbert's reinterpretation idea caused a big clash.
Oh, yeah, huge clash.
Because for Frege, each thought had a fixed subject matter.
Right, it was about something specific.
And so reinterpreting a thought just didn't make sense.
It was like speaking a different language.
Right. Like you can't just change the subject.
Exactly.
So when Hilbert reinterpreted point as a pair of real numbers, Frege saw that as shifting the focus to a completely different set of thoughts.
Yeah, instead of thinking about points and lines, you're now thinking about real numbers.
Which are totally different.
Completely different subject matter.
And Frege felt that just because these reinterpreted sentences
Yeah.
happen to express true statements about real numbers,
Right.
that didn't tell us anything about whether the original geometric thoughts.
The ones about actual points and lines?
Yeah.
Yeah, he thought that was irrelevant.
It was like a magic trick.
Yeah, a bit of a mathematical sleight of hand.
Okay. And it wasn't just the reinterpretation issue.
Right.
Frege also questioned why we even need consistency proofs in the first place.
Yeah, why bother proving consistency if the axioms are already true?
Right, because from Frege's perspective, the axioms were supposed to be expressions of true thoughts.
About the world.
Yeah.
So they should already be consistent.
Like inherently.
Inherently true statements can't contradict each other.
Right. Truth implies consistency.
Exactly.
But Hilbert,
Yeah.
he had a different view.
Yeah, for him, axioms were more like starting assumptions.
Okay.
Postulates.
And their consistency wasn't guaranteed.
It had to be demonstrated.
That's a huge difference.
Huge, yeah. It shows you how different their philosophical starting points were.
Okay, and then there's this whole thing about the connection between consistency and existence.
Oh, yeah, that's a big one.
So Hilbert believed
Yeah.
that if you could prove a set of axioms was consistent,
Yeah.
that meant the mathematical entities they described.
Right, like the points and line.
They actually existed,
At least in the mathematical realm.
at least in the world of math.
Yeah, but Frege strongly disagreed.
Of course he did.
He said consistency doesn't equal existence.
So just because you can't derive a contradiction,
Doesn't mean the things are real.
and he uses this great example.
Oh, yeah, the intelligent, omnipresent, omnipotent being.
Right, you could have a set of sentences like, A is intelligent, A is omnipresent, A is omnipotent.
And those sentences might be consistent.
Yeah.
But that doesn't mean such a being actually exists.
That's a good example.
It's a classic.
Because it's so clear.
It's very intuitive.
So I guess at the heart of their disagreement
Yeah.
is this question about what axioms are.
Yeah, like what are they really?
Are they true claims about a fixed subject matter?
Like Frege thought?
Yeah.
Or are they more like these sentences that can be interpreted in lots of different ways?
Like Hilbert's love law chimney sweep.
Exactly.
So it's a clash between a more traditional view of math.
Yeah, describing specific domains versus this newer, more abstract structural view.
And that debate is still going on today.
Oh, yeah. Philosophers of mathematics are still arguing about this.
Right, because it gets at the heart of what math is all about.
Absolutely.
Okay, so Frege, he was really concerned that just because a reinterpreted set of thoughts,
like the thoughts about real numbers, is consistent.
doesn't mean the original thoughts are consistent.
Right, because they're about different things.
And he used this analogy of special geometries and the general case.
Oh, yeah, that's a good one.
So he's saying, imagine you have this general set of axioms
Yeah.
that's supposed to describe some domain.
The general case.
Right, and then you look at specific interpretations of those axioms.
In different domains, these special geometries?
Right, like if you reinterpret point as a pair of real numbers, that's a special geometry.
Exactly.
And Frege's point is that just because one of these special interpretations is consistent doesn't guarantee that the original general case is also consistent.
Right, because there might be hidden contradictions.
That only show up in the general case.
Exactly.
Okay, but Hilbert's counter-argument was that consistency is about the structure.
The abstract structure defined by the axioms.
So if one interpretation is consistent,
any interpretation should be.
Because they're all capturing the same underlying structure.
Exactly. It's all about the relationships, not the specific objects.
Okay, so that's the core of their disagreement.
I think so.
Two different ways of looking at what math is.
And how we know what we know in math.
Okay, now the encyclopedia talks about different ways to interpret Frege's rejection of Hilbert's approach.
Yeah, there are a couple of main interpretations.
Okay, let's hear it.
So one interpretation is that Frege just didn't get it.
He didn't understand what Hilbert was doing.
Maybe not fully.
Okay.
Like maybe he didn't grasp that Hilbert's formal system really did have implications for the thoughts.
Even though Hilbert wasn't explicitly talking about thoughts.
Right. Hilbert was all about the symbols.
And Frege was all about the thoughts.
Exactly.
So maybe there was a disconnect there.
Maybe.
Okay.
So on this view, Frege's objections were kind of misguided.
Because he missed the connection between the formal system and the content?
Yeah, the semantic content that he cared so much about.
Okay, but there's another interpretation.
Yeah, a more charitable one, I think.
Okay.
Which suggests that Frege and Hilbert just had fundamentally different understandings of consistency and independence.
Okay, so it's not that Frege misunderstood.
Right.
It's that he was talking about something else entirely.
Exactly. So for Frege, whether a thought follows logically from other thoughts wasn't just a matter of the formal structure of the sentences.
It wasn't just about the symbols.
No, it also depended on the content of the terms.
The meaning.
Meaning, yeah. So you couldn't just swap out words.
Even if they had the same grammatical role.
Right. Even if they were both nouns or whatever.
Frege would say, no, no, no.
The meaning matters.
The meaning matters.
And this is what's called a content-sensitive understanding of provability.
Okay, content-sensitive meaning.
Meaning that the actual concepts involved are crucial.
Not just the formal relationships.
Exactly.
Okay, and the encyclopedia gives this helpful example.
Oh, yeah, I like this example.
Consider the sentences, point B lies on a line between A and C.
Okay.
And point B does not lie on a line between C and A.
Okay, so those sound equivalent.
Yeah, but Frege might say, no, no, no.
They're different.
Because for him, the concept between implies a specific order.
Right, like A, then B, then C.
So the second sentence would be a contradiction.
Even though formally it looks fine.
Right, because the formal system doesn't understand the concept of between.
Exactly, it's just manipulating symbols.
But Frege is saying, no, no, no.
We have to analyze the concept itself.
And that gets us back to his whole logicist project.
Oh, yeah, where he was trying to break down all these mathematical concepts.
Into their logical foundations.
Exactly, like what does it really mean for something to be a multiple of something else?
Right.
He wanted to find the logical core of these concepts.
So for Frege, you couldn't just look at the formal system.
No.
You had to really dig into the meaning.
You had to do philosophy.
You had to do philosophy.
Yeah, you had to analyze the concepts themselves.
Okay, now the encyclopedia also mentions this later proposal by Frege.
Oh, yeah, in 1906.
Where he tries to come up with a way to prove independence.
Which is interesting because he was so critical of Hilbert's approach.
We'll know what's going on there.
So in these later writings on geometry, Frege sketches out this method for showing that a thought is independent of other thoughts.
Okay.
And his idea involves creating a mapping.
A mapping?
Yeah, a way of translating terms into other terms.
Okay.
But this mapping has to preserve the syntactic type of the terms.
So nouns map to nouns, predicates map to predicates.
Exactly, you got it. And importantly, all the logical terms stay the same.
They don't get reinterpreted.
Nope, they're fixed.
Okay.
And then he says a thought S is independent of a set of thoughts, C.
Okay.
If you can use this mapping to make the sentence expressing S false.
Okay.
While keeping all the sentences expressing the thoughts in C true.
So it's like Hilbert's reinterpretation.
Yeah, it's very similar.
But with this extra constraint about the logical terms.
Right, and the encyclopedia points out that this is really surprising.
Why?
Because it looks a lot like Hilbert's method.
Even though Frege was so against it before.
Yeah, it's a bit of a puzzle.
So did Frege ever explain this shift?
Not really, no.
Okay.
The encyclopedia says that Frege himself thought this method was incomplete.
Like it didn't quite work.
Yeah, and he never really developed it further.
Right.
And then a few years later, he even wrote to this logician, Philip Jourdain, and said that he didn't think you could prove the independence of the parallel postulate.
Oh, wow. So he went back to his earlier view.
Yeah, it seems like it.
That there's no way to prove independence.
At least for this particular case.
So even Frege had trouble reconciling his philosophy with the practice of math.
It seems like it, yeah, it's a tough problem.
And this tension between formal methods and philosophical analysis.
It's still alive today.
Oh, yeah. It's a big debate in philosophy of mathematics.
Especially when you talk about structuralism and the foundations of math.
So Frege and Hilbert, they might be gone.
Yeah.
But their debate is still shaping the field.
Absolutely.
Okay, so looking back at this whole controversy.
Yeah.
Who would you say won?
In a practical sense.
Yeah.
Hilbert won.
Really?
Yeah. His ideas about consistency and his methods for proving it.
Yeah.
They've become the standard in math and logic.
So even though Frege raised all these important philosophical points, they didn't change the way mathematicians actually do math.
Not really, but they did make people think more carefully
about the assumptions underlying Hilbert's work.
Exactly, and they highlighted this difference between formal provability and a more content-sensitive notion of logical implication.
So Hilbert might have won the battle.
Yeah.
But the war is still going on.
The philosophical war, yeah.
Okay, so to sum up for you listening.
Yeah.
The key difference between Frege and Hilbert is this contrast between a formal understanding of axioms and proof and a content-dependent understanding.
It's all about meaning for Frege.
Right. And this wasn't just some technical argument.
No.
It was a fundamental clash about the nature of math.
And how we know mathematical truths.
So I think the takeaway here
Yeah.
is that even in a field like math,
Yeah.
where things seem so certain,
Yeah.
there's room for these deep philosophical disagreements.
Absolutely, and that's what makes it so interesting.
Right, and by understanding these historical debates,
Yeah.
we get a better appreciation for the complexity of these seemingly simple concepts.
Like consistency and proof.
Yeah, like what does it really mean to prove something?
It's not as straightforward as you might think.
So here's a question for you to ponder.
Okay.
In our world today,
Yeah.
where everything is becoming more formalized.
More algorithms, more data.
Yeah, does the meaning of our fundamental concepts still matter?
That's the big question.
Like if we could build a system that's consistent and it works,
Yeah.
does it matter if we understand the underlying concepts?
Or is that just extra baggage?
Right.
It's a tough one.
Yeah, it is.
And it's relevant to so many fields.
Not just math.
Like AI, ethics, everything.
So maybe Hilbert's victory in math
Yeah.
doesn't mean that philosophy is irrelevant.
Maybe there's still a role for philosophical analysis.
Even in a world of formal systems.
I think so.
Something to think about.
Definitely.
And if you want to delve deeper into this,
Yeah.
I highly recommend checking out the Stanford Encyclopedia of Philosophy entry.
Good place to start.
Or reading this.
Oh.